There we go.
Any questions?
Yes. Number 49 on the textbook homework.
Which one was that?
It's
I
the,
meant to grab the textbook, but I forgot.
so it's like the three charges and they're in a triangle. It's like the above the negative x-axis.
Alright, so charge here, here, and here, equilateral triangle.
Yes.
And you're supposed to find the electric field at this point?
Field at the top charge, yeah.
Okay. And 10 centimeters apart?
Yes. And one of the charges is 10 microcoulombs. And the other one is negative 5 microcoulombs.
Something like that. If my charges are backward, then there are points in the other direction. All right, so I know the electric field goes away from positive. So my electric field will be going in that direction right there. Since it's an equilateral triangle, I know that's a 60-degree angle. Going in this direction, I know the electric field goes towards the negative charge. And so that would also be a 60-degree angle because it's an equilateral triangle. That's 60. So the equilateral 60, 60, 60. You need some of those?
Yes.
Who's gonna need a calculator in here? You know. Well, how many do you need?
We'll see. When are they?
Probably in about 10 minutes. Well, there's 2 questions, so I don't know, sometime 10, 15 minutes.
Okay. We will have a fight to the death over who gets the calculator.
We can take them.
I got
You do. But it's that dilemma in fail-safe, you know, the accountants versus the hard criminals.
true. Very true.
Sorry, you were the hard criminals in that, in case you're worried I was comparing you to accountants. In fail-safe, it was a question of if the US and the Soviet Union with the nuclear were the only people who would survive with the hardened criminals who were protected by walls and the accountants who would be protected by papers. And the hardened criminals would have the brutality needed to survive, but the accountants would have the organization, so who would win? But it's a good thing I recorded all this. All right, so figure out what the 2 electric fields are and add them together. The third charge is not contributing any electric field at its location. And so we end up with the magnitude here, the magnitude of the electric field, KQ over R squared. And this would be Q, I'll put Q positive. Thank you. KQ negative over R squared. Monkey chug, 9 times 10 to the 9th, times 10 times 10 to the negative 6th, over 0.1 squared.
Now, there was a correction in the notes for 49 that said to essentially replace 60 for 120,
The degrees.
the degrees.
Oh, all right, so
What is that? Scale.
do they have the plus and the minus swapped? If the positive were here and the negative charge were here, then the electric field would be going in those directions. So that would be 120 degrees.
Yeah,
But if the positive charge is here, it's going like that, then it's just a 60 degree angle.
okay, so the way they have it, it's, the positive's on the right. Where?
Yeah, apparently in the solution.
Yeah.
And in the picture, it was on the left.
Well, no, in the solution, it was done as if the positive was on the left. In the actual image.
Oh, okay, substitute, put 120 in 460.
Yeah.
Okay. So,
Got it.
all right, this, so that ends up being 90 times 10 to the third, 90 times 10 to the fifth, or 9 meganewtons per coulomb. Unless I made a careless error. Ethan, you're squinting as if you're,
I can't read the board.
oh. That should be a whole lot clearer there with the,
What is that next to the meter newton per coulomb?
what is that?
Is it just
That's a mega, 10 to the sixth, meganewtons per coulomb.
Well, you have 90 to the 10 to the 5th. Or do you add one more?
So I get 9 times 10, which is the 90,
Uh,
10 to the ninth, 10 to the sixth, or negative 6 is 10 to the third.
yeah,
So that would be 90 times 10 to the third.
yeah.
I'm dividing by 0.1 squared, which is dividing by 0.01, which is the same as multiplying by 100. So that's why I got 10 to the fifth.
So what is that next to the meganewton per coulomb?
The 9.
Oh, is it, are you saying that 90 times 10 to the fifth is the same as 9 meganewtons per coulomb?
90 times 10 to the fifth is the same as 9 meganewtons. Would you prefer 9 times 10 to the sixth newtons per coulomb? Okay. I thought I'd save ink, save a tree, or a dinosaur, or whatever goes into this. All right, the other one, well, the distance is the same, k is a constant, and the only thing that's different is the charge and the negative, but the magnitude here would have to be half of that. So 4.5 times 10 to the sixth newtons per coulomb.
Would that be for the one going down?
Yes, yeah. The magnitude of the E negative. and E positive.
So the total would be 9 times 10 to the sixth units per coulombs, and then each one is 4.5.
You confuse me. 9 is the magnitude of this electric field, 4.5 is the magnitude of this one.
Oh,
We're not done.
okay.
I feel like there's a uncertainty in there. There's a question.
That makes sense. And then, okay. Never mind, because I just saw the 9 and then 4.5, and I assumed that we just cut it in half.
Only cut it in half because the electric field from a 5 is going to be half that of a 10.
Okay.
All right, so now I have two vectors that we're adding together in polar notation. Yes. Sorry about that. All right, so I'm adding, the math problem I'm dealing with here is 9 times 10 to the 6th newtons per coulomb, 60 degrees, plus 4.5 times 10 to the 6th newtons per coulomb, negative 60 degrees. That is the math problem I'm working. Again, under the math assumption that 0 degrees is to the right, 90 degrees up, 180, 270, and then negative going the other direction. Questions about this up to here? Not this, but anywhere up to here. All right. There are a couple ways of going about it. We can just set up a bunch of two right triangles and get the components, or we can do the blind method. I got a 10 to the 6th newtons per coulomb there. I'm just gonna not write 10 times 10 to the 6th till I get to the answer. I'm just gonna leave that off to the side. So I get 9 cosine 60 degrees. I hat, J hat. I hat plus 9 sine of 60 degrees, J hat plus 4.5 cosine of negative 60 degrees, I hat plus 4.5 sine of negative 60 degrees, J hat. So that's sort of the blind method where if you have it in not just the base angle, but the total angle of 60 degrees, negative 60 degrees, and I hat, J hat, then you can just plug straight in like that. So this becomes 4.5 I hat plus whatever that is, plus 2.25 I hat.
What's the math for that?
Pardon?
9 sine 60?
Yes.
7.79.
What is this again?
7.79.
7.79 J hat minus 3.895.
$3.897.
7. All right, add like components. So I have 6.75 I hat plus 3.897-ish J hat. Now I haven't put the units back in, and don't forget I had that 10 to the 6th. So 2 times 10 to the 6th.
Did you forget the other J hat?
No, this should have been half of that. So I figured that it's just, since that's positive, that's negative, it's just that positive. There could be some rounding issue there.
In what situation do you subtract these vectors?
Well, one is going up and one is going down, so since they're in opposite directions, there's gonna be either the addition of a negative number or a subtraction, whichever way you like to look at it.
How did you decide to do cosine or sine?
When you set up I hat, J hat, with basically the same coordinate system as you have up here. I have my angle set based upon right horizontal. And so there's my I hat right there. J hat, I go up just cause. Once I do that, that establishes that's positive 60 degrees and that's negative 60 degrees. And then when you're breaking it up, it's gonna be, given the way I've set up I hat, J hat, it's cosine of the angle and then sine of the angle. If that had been 100 degrees, I just stuck 100 degrees there and there. Is that sufficient? Okay. questions on this?
Oh, is that the final answer?
It asks for what's the electric field, right?
Yeah.
Done. If the second part's asking what is the force on that charge, well, then I'm just taking that charge and multiply times the electric field. Because this tells me the amount of newtons for every coulomb of charge bathed in it.
So writing that out with the 10 to the 6th Newton coulombs,
Per coulomb.
newtons per coulomb. So it would just be the same thing as saying, okay, 6.75 times 10 to the 6th newtons per coulomb I have plus 3 point. You could just put it.
Yeah, I could have put it here and here.
Okay. Which per convey, okay, I got you.
And normally I would, just that it wasn't my move this morning. So that,
When you were just talking about part B, the force, which number would you use? Would you use I hat and J hat?
yes, the force is a vector, so it has components.
So you just do the equation twice and then add those up?
Do the equation twice.
The force equals Q over,
The force would be Q, or whichever Q, E.
Okay.
So the force on charge Q is equal to charge Q times the electric field that's at that point. So the electric field at the top, we've just solved over there,
Yeah.
so whatever, so now I can, whatever charge I put here, I just multiply times that electric field and I get the force.
okay.
Where is the textbook? Because I'm trying
Where is the textbook?
to in the Blackboard.
In the syllabus, there should be a link to the textbook.
Yeah, there's no link on the, online, not online resources. The course material, or
There's
it was
no-
last semester,
So there was one last semester,
I think so. That's where I found the textbook last semester.
under the syllabus?
No, under the, course material, I think.
It was supplementary course materials.
No, okay. Well, we'll see if I remember to put that in for this. Yes, Ethan?
So, there's multiple problems where you find two forces and you have to find the total by subtracting one from the other one. How do you know which one to put first?
Which one minus, it depends on which direction you consider the positive direction.
So you put the one that's in the positive direction first?
I would, I mean, you could do, like, if I have to find the difference between 1 and 2, I could do 2 minus 1, 2 plus -1, -1 plus 2. I mean, you've got options. I feel like there was more to that question than my answer.
No.
Is it? Okay. Other questions?
Ibrahim,
So this has a diagram with it, but to my memory, the diagram is just the line, and then we have at 3, at 8, and at 11. And so we're asked, what is the force on the charge located at x8? Right, this is 8, this is 3, this is 11. And given that Q equals 1 microcoulomb,
Right. Presumably they give you the other 2 charges? Is ultimately how to solve it, or how, do you have another question in there?
in the work shown, there's this -2 that comes up, and I have no idea where it's come from.
All right, I think it's come down to this. I'm gonna go grab the textbook.
Thank you.
I'm just gonna let it run.
Way to go, Ibrahim.
which problem was it?
41.
Alright, what is the force on the charge located at x equals 8 centimeters, given that Q, oh, okay. So they tell us that we have a number line here, and this is 3 meters, 8 meters, and 11 meters. This is charge Q, this is negative 2Q, and this is Q. So that's given in the problem.
Oh, so then, okay, I see where the negative 2 comes. You're just multiplying Q, which is 1 times 10 to the negative 6 coulombs by negative 2.
Yes.
When you put it into the equation.
Yes.
Okay. Okay.
Alright.
And also, towards the end of the problem, it just says 12.8 newtons to the right. How did we know that it's to the right?
Well, I know that this distance here is less than this distance. So this will have a stronger force than this will.
Right.
So, this is being attracted this way and that way, and we're trying to draw arrows with some semblance of relative size. So there's gonna be a greater force to the right.
Okay.
That's how you would know.
And then the same kind of thing happened on 32, where it said it just, I mean, if they did the math, and then they just added east.
Find the direction and magnitude of an electric field, so magnitude and direction. So sorry, what was your question again?
So they get to the answer,
Right?
the magnitude, which makes sense, but then they just say east at the end of it.
Yeah, because in problem 32, the wording is, they talk about a westward force. So that's why they're using west or east as directions in the end.
A westward force on an electron would be in eastward facing